Good day and welcome to today's class. So we want to look at a concept of numbers called the number systems. So when we say number systems, we mean the concept involving the six conventional numbers in the world. Before the advent of number systems, the artifacts such as wood, stones have been used for counting or measure or label quantities in the early days. The most natural examples of these number systems is what we refer to as the counting numbers. Counting numbers, otherwise known as the natural numbers. I will refer to them as the number one, two, three, dot, dot, dot. That is, this goes to a larger number called the infinity. Okay, so this notion of the natural numbers, okay, or positive integers, has been extended further to a number called the whole numbers. This whole number is with the inclusion of the number zero as the beginning of these counting numbers. Okay, and this has also been extended to the number integer numbers. That is, if we extend this further to a negative number, okay, okay, so these are integer numbers. This concept again has been extended to a number called the rational numbers. This number involves a numerator and denominator, such as the number 1 over 2, 2 over 3, and what have you. This notion is not stopped there. It has also been extended to the number called the irrational numbers. Okay, and these irrational numbers are numbers such as the square root of 2, the number pi, the number exponential, and the number golden ratio. That is, the number will go from the Fibonacci ratio, okay, whose symbol is 5. Okay, so this doesn't stop there. Okay, the notion again has been extended to a number called the real numbers. These real numbers combine both the rational and irrational numbers, okay, and form a line, a thin continuous line, okay, without breaking. This number constitutes what we refer to as this line. That is our number line or the counting line, okay. Okay, it doesn't stop there again. The notion of the real numbers has also been extended to the larger system, okay, which we refer to as the complex numbers. This complex number actually take the real number line, okay, to a square root of -1, okay, and this number can be found on a vertical line as this, okay. This square root of -1 and the number we refer to as the number I, okay, they are imaginary, that's why we label them I, and they can only be found here, okay. For example, I, 2I, and so on and so forth, okay. So now the number system, as we have said earlier, we have mentioned about six conventional types of numbers. That is the natural numbers and the symbol called the glyph symbol that is given to each of them. Okay, let us write this out for proper understanding. So the first conventional number, as we have said, is the natural numbers. The natural numbers. Okay, and there is a symbol given to this. Okay, this symbol is actually coming from the glyphs notation. Okay, and the first known place where this kind of symbols is emanating from is the West Asia. Okay, and we have also said that we have the number integer numbers. Okay, and this symbol was given to this. Okay, the symbol Z there is a notation for whole numbers in the in German. Okay, and we also have the number rational numbers. Okay, and this notation is given to this. Okay, from the word quotient, and also we have the number irrational numbers. Rational numbers, and this is the notation I from the word irrational, and we also have the real numbers. Okay, this is otherwise known as the counting numbers. Okay, so from the word real, we have this R. Okay, the in the glyph notations. Okay, we also have the complex number, which we refer to as the most largest number in the world of mathematics or in the entire number system. Okay, and from the word complex, we have the symbol. Okay, also the in a glyph form. Okay, so these are the 6 conventional numbers that we have. Okay, but in this class, we want to be looking at the properties or the attribute of each of this number. Okay, how they differ from one another, or how larger they are to uh, one another. Okay, so we want to start with the natural numbers. Okay, so let's give what is a natural numbers, and let's first look at some of the attributes of this number. So now the natural numbers. So as we have said, the set of natural numbers is defined as the set n equal to the number 1, 2, 3, so on and so forth. Okay, this is actually going to a number called infinity. Okay, in an integer form. Okay, so when we look at this number, we have said this number is otherwise known as the counting numbers. Okay, this is the most natural examples of any types of number that one can think of. Okay, so what are the attributes or properties of this number? Okay, so we know the properties of this number by uh, the basic operation in mathematics, which is known as the addition or the subtraction or multiplication or division and other forms structures such as the exponent, if at all this has it, or the order. Okay, so these are the things we'll be looking at here. Okay, but for these natural numbers, we have three basic properties for this. Okay, three basic properties which can be elaborated further. Okay, and the first one among them is the closure property. Okay, so we refer to this as n1 to mean the first properties of this number. Okay, so what this is saying is that if we have two numbers in the set where this number are distinct numbers, okay, then under the operation addition, this is closed. Okay, as this connotes, if you pick any two number here and we perform the operation addition on the two numbers, okay, such addition or the sum of this number will always be in len. Okay, and in mathematics we refer to as this as the closure property under the addition. Okay, so this is the first operation we have noted for this. Okay, the second property, okay, that one we think of is the that of the subtraction. Okay, but we will observe that the subtraction cannot hold for this, and the reason is not far-fetched. If, for example, we pick two numbers here, let's say m is 1 and n is 2. If we subtract this this by saying 1 minus 2, that will give us -1. And in all of this set, there is nothing like -1. And because of that, the operation subtraction cannot hold for this. Okay, so we skip that. So let us go to multiplication. Of course, that we hold there. That is, if you pick any two numbers in the set n, okay, when we perform this operation, we refer to this dot as the multiplication sign. Okay, this also will be in the set of natural number. Okay, also this property also is here. And again, after the multiplication, you see that the fourth operation of this of the basic operation in mathematics is division. But such division cannot hold there. Okay, so it suffices for us to pick two numbers. Let's say m is 1 and n is 2. Okay, so if you perform this operation 1/2, that will give us in decimal 0.5. And everywhere here, such a number is not there. In fact, this number are integer numbers throughout, positive integers. Okay, so subtraction can hold in this set, and division cannot hold. Okay, so and because of that, we limit the operation to these two. Okay, though there are other properties such as the exponential of an integer, okay, that will give us a positive integer. Okay, that for example, if we consider an integer number and raise it to a power of an integer number, okay, this we hold. Okay, but that is not where we are going. Okay, we are just looking at the basic properties of this number. Okay, and the third one we will think of here is that if we also, this time we have the order property. Order, that is the order of this number. That is, or let's say for any m n in n, that is, if you pick any two numbers here, okay, two things can happen. Okay, we say either m is less than n or m is greater than n. Okay, if you pick any two numbers here, okay, this order can happen, but this order, okay, can also happen. As we can see, let's pick any two distinct number, 2 and 3. The number 2, if it is m, is less than the number 3, if this is n, and the other way around too. Okay, this is actually rules. Okay, so because of this, these are the three basic properties that we have noted for this. Okay, there are other properties, okay, embedded in each of these property. Okay, let me make that statement. Okay, here. So when we get to a larger number, okay, a larger set of numbers, okay, so we'll talk more on that. Okay, let's quickly make that remark for addition. Okay, we have referred to this as closure property under the addition. Okay, that is, this happens, and of course commutativity also happens here. What we refer to as commutative is that under the addition is that if you say m plus n, okay, it's a certain number, okay, we can pick that this m plus n, even if you alter make the reverse of such a number, okay, this will equal. Okay, under addition, we refer to this as commutativity. Okay, so also if you pick any three numbers here under addition again, three number, let's say this time m n o. Okay, so this operation is also true. Okay, that is if you add these two numbers, then add it to zero to o. Okay, this is o, not zero. Pardon, please. So this is similar to n plus o. Okay, this is similar, and we refer to this as associativity property. Okay, and here also commutativity also is there under the multiplication. That is, if you say m times n is equal to n times m, okay, it's suffice to also pick two numbers and test that. Okay, I'm using the feasible number that we can see here. Of course, we also have the number 5, 6, and so on and so forth. So we pick two numbers here and say 2 times 3. Okay, even when you reverse it, both the results are the same. Okay, so commutativity also is there, associativity also is there. That is, we have three numbers and we group this number 2, then add multiply it with another the 1. Okay, perform otherwise in the right hand side equality there. So we see that the result will be the same. Okay, and there is a property that combines these two together, and we call that the distributive property. Okay, this distributive property is talking about when we have three numbers, okay, and then we are multiplying such a number with the addition of the other two. Okay, of course, when we open the bracket here, perform the use of our bird mass. Okay, when we open the bracket, this will be nothing but m dot n plus m dot o. Okay, so refer to this as the distributive property. Okay, so anytime we are referring to a concept like this in mathematics, okay, we should also know that this notion can be extended to something like this. Okay, the fifth or the fourth, okay, one, two, three. Okay, the fourth that we can also note here is the identity property. Okay, the identity property owes here. Okay, under addition. Oh, pardon. Identity properties did not hold here. Pardon, because the number that we can refer to as the identity should be zero here, and zero is not part of this. Okay, so we can't say identity holds here. Okay, but we can say for multiplication identity holds, because if you pick a number here and multiply the number with a number 1, okay, in which the identity here is the number 1, okay, so this is going to give us the result m. What we are saying here, what we mean by identity is this: if you multiply, perform an operation of a number with a number and give you the same number, okay, what is happening there is identity, and the identity number is 1 here. What we are saying here is that for us to have m plus a number and give us m, that such a number must be 0, but 0 is not part of the set. So identity under addition does not hold for natural numbers, but identity under the multiplication holds, because we can find the number 1 that when multiply with m, we have m. Okay, so that is that, and I think the other thing is the inverse number. Also, the inverse also for the addition of the natural number. Inverse means when you add a number and an inverse of it, okay, the result will be 0. The result being 0 is not part of the set, and of course we can make use of such property. Okay, however, for the multiplication, okay, inverse hold for only the number 1. Okay, inverse hold for only the number 1. Okay, so that is that. We'll make this property more elaborate when we get to like we said, a larger system of number. Okay, and these are what we have noted on natural numbers. Anytime you think of the counting numbers, okay, think along with all these property. Okay, this three property which is basic, and then of course these sub properties. Okay, and here too we also have some of the properties too. Okay, this also holds for addition. That is, we have four numbers and such a thing happen there. Okay, we can add a number to this, and this maintain, preserve the order. Okay, so but when we get to a larger system, we talk about. So uh, before we leave these natural numbers, we quickly want to add one particular number to this set. Okay, because this number, okay, which is called zero, when it is added to this natural number, okay, it makes this natural number a whole numbers. Okay, so the number zero, when it is introduced here, okay, we call this natural number a whole numbers. Okay, or non-negative integers. Okay, so let's make a clarification here before we quickly leave. So let us for this place. Okay, we now change the symbol to n naught in order to accommodate the number, and we refer to the set of whole numbers as this. Okay, the major difference between this and this is not far-fetched. It is this zero, and because of that, let me I will say the name that we are calling this. We call this the counting numbers or natural numbers or positive integer numbers. Okay, three names here. Okay, for this natural number. So now when we get to this, okay, I think there are two names for this. Is that we call this whole numbers. Is that we call this whole numbers or non-negative integers. Non-negative integers. Non-negative integer numbers. It's okay. So these are the name we have attributed to this. Okay. So the same property that holds for this natural number also holds for these whole numbers. Okay. Just that there is a when we are talking about uh, the first property under this, okay, in one of the sub property, okay, under the identity law will say does not hold for this, okay, under addition, but it will hold for this, okay, because with the inclusion of zero, okay, we can find the number that when we add the number to zero, okay, we get that number back, okay. For example, if I pick any m, let's say any number m in n naught, okay, if you add this m plus zero, okay, this is same thing as this under commutativity that we have said earlier, and this will be m. Okay. Okay. So in this case, we call this zero an identity number. Okay. And because of that, identity law owes under addition for this, but it does not hold for this as well. I've said earlier. Okay. So these are one of the major difference between this and this. Okay. In mathematics, this is more useful for discussing algebraic structure in mathematics than this. Okay, because of the inclusion of zero. Okay, so like I said, all the property that was for this also for this. Okay, just that this one has increased with one number, and of course that has to change the structure of this number. Okay, so another thing we want to note here is that under multiplication, if we have two numbers in n naught, okay, we also know that zero divisor, this number has no zero divisor, okay. if you pick any two numbers here, and when we perform the operation, that multiplication, and the result is zero, okay, how do we conclude this? We conclude this by saying either n is zero or n is zero, okay? Because if n, when we pick any two numbers here, if n is zero and you perform this operation by saying zero multiplied by n, whatever n is, of course that will be zero. And again, if n is what is zero, okay, by the virtue of what we have here, okay, so by virtue of that, we'll say that this uh, zero multiplied by this m, whatever this is, this actually be zero, okay. So and because of that, we also remark that this has no zero divisor, okay. This has none, whether zero or no zero, this one has none, okay. But we can say that for this because with the inclusion of the zero, okay, it makes more sense to talk about the zero divisor, okay. So this is a number, the whole number, okay. And then we have said is similar to this number, just that this number has one number more than this, okay. And a simple remark we'll make here is this, that number this number n, okay, is simply a subset of this, okay. Is only contained there because the answer is simple. The entire real number is this, okay, and it means the entire real number is inside there, okay. And because of this, let us make another uh, simple mathematical expression, that this number is equal to the number n, okay, union a singleton number 0, okay. So this is a set of one number 0 union the natural number, give us the n naught, okay. This is that under the natural numbers, okay, and the whole numbers, and this is how we uh, uh, I mean, these are just a simple relationship between them. Okay, in our next class, we'll talk about the second concept of the number called the integer numbers. And of course, let me give us just a tip of that. Okay, when we extend this to negative integers, okay, that becomes a set of integer numbers. And of course, we have included more numbers to this, that will make the properties more of such a number more elaborate than what we have here. Okay, so until then, bye for